Okay, thank you very much. And we're now going to start our last session of the day. So for me, this was the one I was looking most forward to because this is a really exciting session. So we're going to be looking at solar, and fusion energy. So I believe that this is probably going to be alien to the majority of us in the audience. So we've got a lot to learn here. These are the guys who are really kind of the edge of the transition of market. Sorry. So our next speaker is Dr. Joven Lim, and he's going to be looking at challenges in Tokamak-type fusion reactors. Before he starts, he gave a brief breakdown of his expertise. So Joven is an experienced nuclear materials scientist with an engineering background. He is a corrosion lead at the STP program. His work experience today has equipped him with an extensive in-reactor material performance evolution background and experience in working in various nuclear industries around the world. He's published over 40 technical report articles and papers on the understanding of material performance of nuclear materials as manufactured, welded, irradiated, and corroded. He's passionate about the low carbon energy future and is creative, innovative, and is also striving for excellence. Joven has a bachelor's, doctor of philosophy, and is a professional member of the Institute of Materials, Minerals, and Mining and the Institute of Physics. He's a core member of the Reactor Chemistry and Materials Research Working Group, the GE Catastrophe for Energy, and also an active member of the International Cooperative Group of Environmentally Assisted Cracking and International Group of Radiated Damage Mechanisms, and the lead for Nuclear Energy Agency Focus Group on transmission electron microscopy characteristics of radiation damage. So with that, I hope that you enjoyed his wonderful presentation. And now,
and the time from overview to listen a bit about what doesn't exist yet. If we don't have a fusion reactor that's running to offer energy across the world, we are going to be there in 20 years' time. I just want to ask questions somewhat about, I believe all of you heard about fusion reactors. There is 2 fusion reactor research reactor in the UK. It's all in Abingdon, where the UK AEA is. I also believe that some of you is a bit more experienced. I'm not going to say old. Probably know UK AEA in past. So UK AEA, last time there's many branches. There's fusion, fusions, and many other things. And then I believe 30 years ago is no longer there's any UK AEA is dismantled. That's NNL. When you start hearing NNL, you start hearing AWE. Basically, they just branch out to spin up another company and on an entity on its own. And UK AEA, this name came back probably 5-6 years ago during the rebranding of Column Science for Fusion Energy. So now UK AEA focus on fusion research, anything about technology required to realize the fusion reactor, UK AEA is doing it. So I'm only talking about a small part of it, which is material related, and corrosion related. So I'll start with a quick introduction about UK AEA Materials Business Unit, what we do, the aim for UK AEA now, private investment, the landscape basically for fusion research and development, the next generation nuclear power plants and how fusion actually fit in. Nuclear reaction, just get us all on the same page, sustainable fusions and harnessing its power. How do we do that? Critical components in a sustainable Tokamak-type fusion reactors. Commonalities between fusion and fusion's corrosion perspective. I know this is quite different compared to what we hear in the morning and in the afternoon. And then the environmental influence factors or corrosion issue in the fusion reactor, what we learned from fusion site and what we learned now, or recently, I should say. And then a case study about when there's presence of radiation, how does it different when it comes to corrosion. UK AEA, we have over 2,000 employees at the moment, and is increasing and growing. And in terms of material scientists, we have about this much, over 100 employees. And then with corrosion or engineer scientists with corrosion background, we have just this tiny portion, about 5 of us. So it's basically what mentioned by Anthony just now. There is a need of increased corrosion scientists, engineers in the fusion landscape. I will tell you why at the in a slide later. So UKEA, there's missions, and the 4 goals. Basically, we want to be the world leader in fusion research and development, enable the delivery of sustainable fusion power plants, drive economic growth and high-tech jobs in the UK, and last, I need to squeeze in here because of the slide, create places that accelerate innovation and development skill people or industry. So this is basically our strategy goal for UKEA. Of course, pair with it, we have our mission, leading the delivery of sustainable fusion energy and maximizing the scientific and economic benefit for the country. UK fusion strategy papers, I'm not going to join it, it's a lot of wording. I believe the slide is going to be shared. So fusions R&D, basically we are kind of in a race with other countries to learn how to harness fusion energy. We also race against climate change because we need more sustainable green energy. We also race to zero carbon. It's all linked together. Based on the survey conducted in 2022 by Fusion Industry Association, it's declared private funding to develop fusion power plant surpassed 4.7 billion. It's a small number compared to other industry, or especially oil and gas, I should say. But that is a big thing for us because there's 139% increase recently on fusion. Just because they see the potential of fusion itself. You can see the timeline of increase of number of private companies throughout the duration when we start recording fusion research. Number of headquarters of the listed private company in the UK, 3. The number of prototype proposed to be built in the UK, 4. There are other countries come to UK actually want to build their prototype in UK, especially around Aberdeen, just because it's a cluster of fusion scientists and engineers around our region. We basically attract other companies to basically come to us to basically learn, develop fusion energy together. Because everyone have different design, everyone have different technology. We just basically want to cross-link technology and learn which one is better and move forward together. So next generation nuclear technology, fusion and fusion. You can see here is that there's a list of different reactors currently being considered design. I think most of you were heard of the small modular light water reactors currently recently been funded. The Rolls-Royce leading the development of it. And then there are other type of reactors on the list that other countries are actively looking to, like example, supercritical water-cooled reactor, very high temperature gas-cooled reactor, we are talking about 800,000 degrees Celsius. Sodium-cooled, lead-cooled molten salt reactor. In the fusions, we have a magnetic confinement, which is Tokamak-type reactor. And we have others as well, I should say, like initial confinement, which is another one of the companies that recently quite big news about their advancement as well. Magneto, inertial, electrostatic hybrid, and the size of it is relative to the R&D capital investment in that particular type of reactors. So nuclear reaction, where fusion. We know all about fission. So I'm going to just focus on the fusion part. Basically, the approach that UKEA is taking is basically trying to fuse deuterium with the hydrogen isotope and tritium, another hydrogen isotope together, create the fusion reactions, and it basically what it forms out of this fusion reactor, apart from energy, is helium and neutrons. So how to make it sustainable and have this continuous fusion energy and harvest them? So you need to have continuous supply of deuterium and tritium during the reactions. Just now, the simple reaction that you saw just now with pre or transmitted after the fusion reactor, we have 2 products: the helium and the neutrons. The neutron is then we harvest. We use the neutrons, bombard with into something that can create more tritium to supply into our fusion reactions. So in this case, we basically have the neutron interact with lithium, and lithium breed more tritium. Tritium we put in the cycle to form the whole product itself. And lithium, in terms of is an element that is abundant in Earth, but I should put a caveat here. It's difficult to harvest, or basically you need to dig it out, or you need to find a method to basically collect the lithium from, example, sea. And we also have the neutron multiplier. We have two types, the beryllium and lead. Both are kind of like have certain percentage on Earth itself. So this is basically on the left-hand side here, your left-hand side here, is a typical Tokamak fusion power plant design. You can see that this pinky donut-shaped thing is the plasma, or the fusion reactions that form the plasma itself. That can go up to 100 million degrees Celsius. We have to use magnetic field to press the plasma very far or away from the wall, because anything touched it melts. And all the components have to be actively cooled. Then leads to the corrosion problem. So this is just a cross section of the donuts. What you have here is that the orange color here is the superconductor. And then you have the structural components basically hold all the components together. What I want to draw your attention is the red tiles. That's our plasma facing component. That's the component that will receive the most heat flux. And the bottom here is the exhaust of the fusion reactors. We call it diverter. So the energy that the diverter receives is 20 megawatts per meter square. If you're not cooling it in that instant. And then of course the exhaust come out, and all other ingredients we use to keep it cool. We also use the first wall to breed our tritium. Then we have little other problem I'm going to talk about it at a later stage. And just bring it as an example, ITER, the currently been built in Cadarache, France. They have designed their whole reactor now. It's also a research reactor, but full size. So what it basically we learn from the design is that just the pipe itself for this ITER reactor is 35 kilometers. And it had about 3,000 miles. That's lots of pipe to inspect, and it will all be activated. So a bit of commonalities between the next generation fusion and fission. We are not much different with other fission reactors. We also consider water as our coolant, gas, liquid metals, and molten salt. Material we choose is also off the shelf. I would say kind of off the shelf, because we do have to do a bit more dedication so that it doesn't cause long life radioactive isotope in the material itself, so that we have to change some of the element, example nickel, molybdenum, and make it so that the steel itself is low activation coil. So the challenges in the development of sustainable to commercial fusion power plant are going to put emphasis sustainable and commercial here, because we need to make sure that we can make many of it, and it can actually contribute long-term, not this generation, next generation, but generation after us. It has a few requirements. Net electricity output, that's all about efficiency, how we extract efficiently. Plant availability, materials we're going to use. Safety, radioactive material to be generated. Example, we talk about lithium. Lithium is very reactive. How are we going to handle it? How do we control it so that it not explode or interact with water and cause explosion? We also talk about tritium. It's the activation version of hydrogen. Of course, last is the tritium sustainability. So we then have the material challenges. The net electricity output, we also need to learn how to control the plasma. So the high radiation tolerance, high temperature superconductor. about plant availability, safety, treating sustainability, we need high radiation tolerance and low radioactivation structural and functional materials. We need to have treating breeder and neutron multiplier. So this is just one of the challenges in terms of like net electricity output. So in order for us to meet these requirements, we need to ensure the high heat transfer efficiency. Basically, one main thing is to overcome the parasitic heat load. We have many technology and systems behind the fusion reactor. Example, tritium recycling system. We need to be able to extract the tritium out when we breathe it effectively. So that's one type of parasitic load back of the reactors. Outlet coolant temperature is strongly related to coolant we chose. Example, if you go with liquid metal, the temperature can reach about 700 degrees Celsius. Large knowledge gap identified for all fusion coolant options, especially liquid metal under radiation environments. The reason why is that there's no fusion reactor. We can learn how materials degrade under fission neutron spectrum, but there's no new fusion spectrum that we can learn from. So we have to accelerate what we learn. This is just a highlight of the conventional Tokamak and Super X, which is a UK design of a diverter. Is basically it reduced a factor of 10 heat load compared to the conventional design. It's a UK design, I should say. And now many other countries would want to learn more from us on how the Super X design, diverter design actually perform to spread the heat load so that we can actually have, instead of a component that lasts 5 years, it can actually last forever as long as we're not heating up, or as long as we actively cool it. Plant sustainability and safety is all about activation radioactivity that we're going to control. So we have to use reduced activation materials, non-magnetic materials preferred, because if the component in the reactor or within the superconductor is magnetic, it needs extra force when we start to cycle the magnetic field. Of course, we have to choose something that abundance. So if you look at this table here, so this is the percentage or relative amount of abundancy of each element and across the Earth. So what we're trying to use, basically, most of them are iron and copper. So it's quite high element. Beryllium is this kind, this level relative to others element. Lithium is also quite a lot in our Earth. So I should also put a caveat here. These are here rarest material metal. These are the metal we use to basically build our superconductor. There are research to push it upwards so that we use more abundance elements for fusion. So in terms of like tritium sustainability, there are many options to go for, but all of it are related to lithium. So we have to find breeder materials that allow us to actively breed tritium with a tritium breeding ratio greater than 1. Because I think most of us hear about this morning about hydrogen, it goes everywhere. There will be a loss in our reactor when we breed it. So we need to make sure that it's above 1 so that we cover the losses of the hydrogen, or in this case tritium, during the breeding scenario. Of course, the materials we use have compatible with, in this case, lithium. It's highly reactive. Not many materials survive when in contact with lithium. And materials must have reasonable tolerance against hydrogen enrichment, low hydrogen permeability. Again, we are breeding tritium and brittle our materials. This morning, it mentioned about hydrogen gas doesn't react, but we are breeding tritium atom. It basically will react with our material, will cause hydrogen enrichment. So corrosion issues in Tokamak, I think many of you kind of like know this very well. Coolant, temperature, stress is big factors. For fusion, we have radiation and magnetic field. And how does it play? If you use the pictures or schematic that the fusion world used, And the coolants, the stress, the radiation, the materials, everything cross more problem across the pictures. And now we're adding another section that out of the screen here, which is magnetic field. We do not know what we will be facing, I should say, but we are researching how magnetic field impact corrosion, because we are actually, it's ionic process, magnetic field will affect it. So this is just a two schematic showing the radiation impact on corrosion behavior. Left-hand side here, this is a schematic diagram showing the common or simplified local corrosions event that occur in metal under aqueous coolant. And right-hand side here is when radiation come into play. So the radiation itself will interact with water, it form radicals, ions, and basically cause species required to accelerate corrosion. At the same time, the highly energetic radiation will also interact with the materials itself. The materials that is not susceptible to corrosion will become susceptible to corrosion, in the sense that it enhances diffusion of certain chemical elements and force them to precipitate out from the alloy or from the matrix itself. It causes depletion of certain elements that actually gives strength or corrosion properties of materials and changes it locally. And because of that, you have more localized corrosion. So this is just a case study that we did at the UKAEA. So we use one of the components, a small component that will be that apply or will be used to build the diverter component itself. So this is a tungsten monoblock that we call it. So basically, it's tungsten materials to basically cope with the high heat flux, and we have copper pipe, a good heat sink materials for us to get the heat out effectively. The problem is that we use copper chrome zirconium alloy because it has better strength than pure copper. So what we have done is that because we do not have a fusion reactor, we need to be creative how you introduce radiation of the same energy and same flux and some of the number of ions per centimeter squared on the materials to basically try to understand how bad it is the material degrade under those conditions. So what we did is basically we used this 6 millimeter diameter we expose a small region of it to water and then even smaller region to just the radiation, so that we learn the radiation corrosion impact and also the corrosion itself and how it actually degrades the changes properties of materials throughout certain exposure. This secondary electron micrograph here showing the region exposed to just the coolant and the region that exposed to coolant and radiation. The bottom tree spectrum here is basically a Raman spectrum showing what type of oxide they are. We have copper and monoxide and copper dioxide, and for the region that exposed to with radiation is copper monoxide. And one thing that I need to draw your attention is this is again before I go to draw your attention is the same region that we just I just showed you, but then this is cross section of the material itself. What you see here at the top here is the corroded copper surface exposed just coolant, and you can see that this darker contrast here, those are copper oxide, and then you can see the dendritic structure going inwards to the materials. And for the region that exposed to radiation as well, you can start seeing outgrowth oxide. What it means is that you are increasing the activity of losing materials under radiations. And at the same time, you also have materials corrode inward as well. So this is just a higher magnification electron micrograph showing the region where you see preferential oxidized grain boundary. And we of a similar area, but so not similar area, same materials exposed to coolant and radiation. The same way we have also preferential oxidized grain boundary, but there are differences. The region that exposed just coolant see dense oxide, which is good. In the sense that the dense is harder for the oxygen travel diffuse into the materials. But for the region that exposed to with radiation, you can see that this preferentially eroded grain boundary here is very porous. Again, translate into diffusion rate is faster, allow water to even penetrate through the oxide layer. This is 2 micrograph, again, coolant exposed to with radiations. This is transmission electron microscopy that you are seeing here. And you can see that when we basically try to analyze the chemical distribution, we know that chromium do form protective layer against corrosion, which is why we put chromium in the copper. And it forms for the materials exposed just coolant, we see that there are good chromium oxide formed at the surface, about half of the copper monoxide and dioxide. But then if you compare to the oxide that grow under coolant and radiation environments, the copper no longer forming protectively. They are precipitated out. So that changed the mechanism that how corrosion actually works under radiation environments. So as a summary, corrosion behavior with radiation is different compared to without radiation. Oxide growth rate under radiation is growing faster or higher. Type of oxide growth is different as well because of the radiation change in localized chemistry. And the density of the oxide layer is also different with radiation. With that, thank you for your time and your concentration to listen through the talk. And these are the people that I want to thank that contribute to all the science behind here. Thank you very much.
Thank you very much, Joven, for that excellent presentation. I'll open up the floor. Do we have any questions for our speaker today? Okay, do we have one?
Thank you very much for a very interesting presentation. Very, I would say, fresh air to see something different than oil and gas industry. Just a quick one, actually. How is the existing developed material, especially the super alloys that are existingly used in fission reactors, are behaving under this? Is that different radiation we're getting, or have you tested them if they working fine, or they are showing similar zirconium?
So the quick answer is that different. Super nickel alloys also behave the same way. Under radiation, it's behave differently. If I'm not mistaken, without radiation, it will form a protective layer. But then under radiation, it will that is based on fusion. It should behave the same way, the same behavior for under fusion environment. It might be worse because we are seeing fusion have higher neutron energy compared to fissions. That leads to another thing that why investor want to come to Japan or build the prototype in the European countries and also US. Fusion is under nuclear. So all the materials developed have to go through the same stringent as fusion industry. We have to understand how it behave, how it break through the lifetime of proposed lifetime of the reactor. Whereas for UK, we take different approach. We understand that fusion is nuclear reaction, but we are not actually producing or generating uranium or isotope that can build atoms. So we take a different approach in the sense that all the materials that expose to fusion reactions or neutron in this case, it will not form highly dangerous isotope that will harm the world. So this is why we take a different approach in the sense that we can learn as we go. We need to make sure that the materials qualify for certain radiation damage. And we need to demonstrate that we have a strategy to learn as the plant in service, in operation. And we just need to make sure that we are able to predict the behavior at the same time.
Just to follow, just to follow on the question from there, what is the prediction that how long we need to learn up to a point where we say that this material is performing all right?
Unfortunately, we are in discussion with regulators. So it depends how the feedback come back, and then we have to demonstrate how far we can predict with confidence. So one is forward to a certain confidence level. Of course, we know the prediction. When you increase the lifetime prediction, you decrease in confidence. So it's the risk that what is appetite in UK, what are the risks that we need.
That's how it goes with all the industries that are safety related. Of course, your prime objective is it has to be safe. Because it took us how many years to come to a point where we are okay with fission or fusion, and really don't want to go back, isn't it?
So I should say that UK regulators, they are open to that. They are really happy that we look into more innovative methods. So it's why investor, other countries want to come to UK to do it here.
And we go to Japan to get the materials.
Okay, do we have any more questions? All the way back.
Hi, Joven. Thank you for your very interesting presentation. My name is CG Banjoran. The test that you ran at the last couple of slides, where you had the coolant barrels of conductive material and also the effects of radiation, what formulation is that coolant?
Sorry, say last one again.
What formulation is that coolant?
The way I understand it,
What's the coolant made of?
there's no coating.
Coolant.
Oh, coolant is water, sorry. It's PWR, we call it coolant, and PWR condition. Pressurized water reactor. 350 degrees, 15 bars, deaerated, and with increased about 10 ppm of hydrogen.
Is there any chemical treatment applied to that?
No, I should say, because for PWR, there's injection of zinc and injection of hydrogens into the system. Of course, we have our things, the water chemistry specification, the control to minimize the project, which is why we literally take what having learned in PWR and apply to fusions instead of do the whole research again. But using the optimized water chemistry is not really optimized for, in this case, copper.
I'm curious to see if there was any effects of radiation of the chemical additives when you were applied. But thank you. Thank you very much.
Okay, we have one more question.
It's not really a corrosion question, but I'm a little bit older than you, and I'm pretty sure 20 years ago we were 20 years away from fusion.
I was going to ask that question to the board, like, how many of you believe you realize fusion reactor, commercial reactor, we realize in 20 years, 30 years, 40 years. What I heard when I started there doing research for fusion, everyone tell me fusion is 60 years ago, always 60 years ago. But there's a UK program called STAT, Tokamak for energy productions. It's a UK funded program. We are aiming to build the first prototype reactor construction on 2030s. So we are not that far.
So what would be, so what have we, I don't say what have we achieved, because it's obviously you anyway. So what, I mean, what is, in terms of fusion then, what fusion has actually ever taken place, I suppose?
So we have a few research reactors across the countries. And one big news, I think, is probably 2-3 months ago, we UK have basically announced we're using the oldest fusion research reactor jet to demonstrate that we can actually generate 59 megajoules of energy in 10 seconds. We can't guarantee we will be able to do continuous 59 megajoules the second after that, but we're quite sure that we can now generate enough energy to make it sustainable. But whether we're doing pulsing, we are doing cyclic, while we're learning how to make sure it's longer pulse, we have to learn assembly. But we know that for that 10 seconds, we keep 59 megajoules.
Sorry, I did give the microphone away, but so have they achieved those 10 seconds?
Yes,
Yeah.
we have demonstrated that now is one of the world record now. So, yeah.
Thank you very much for the question. Do we have any more questions? Steve, here we go.
Just have one very skimming tape. On your slide, you mentioned materials should have reasonable tolerance to hydrogen equipment. Could you just expand and define that?
Sure. It's so all the materials in the reactor will suffer radiations damage. It will have corrosion issues and you have hydrogen issues. For us, when we put these three problems together, which rank the priority? Radiation is a priority because no matter how good is the material put in, it will change because of radiations. So that's our priority. The materials have to be some sort of have good tolerance. Then the second thing, which is why then comes the hydrogen enrichment, because hydrogen travel everywhere. No matter if you put a hydrogen barrier coatings on it, because the presence of radiation, it changes properties. So it's why we have to understand to use material with certain tolerance against hydrogen enrichment, because it will change. Then corrosions. As a material scientist first, then corrosion scientist. I want to say that corrosion is more a surface issue. If we can make sure that structural materials, the structural integrity part of the components survive, we can deal with the corrosion with it.
Thank you.
Okay, do we have any more questions online? Okay, just got one more.
Thank you for a really excellent presentation. I hadn't thought of this until your talk, but is there a difference between hydrogen embrittlement caused by tritium or deuterium and normal hydrogen? Or do we know?
We don't know. That would be my answer. We do not know. But then we have literally a few groups of people in UKDA looking into this, and around the world, everyone's looking into the differences. But one thing we know, hydrogen, deuterium, tritium diffuse differently because they are different size itself. So that we know that there are different diffusion rate, permeation rates, and we just need to understand how that reflects when we do research on hydrogen, and then learn how to do address that issues.
Just leading on from that, would the difference in the molecule sizes also have an impact on the cracking rate?
I believe so. And because we also haven't talked about hydriding, like the chromium, things like that you mentioned. So hydride formation will lead to that big issues. So we have to basically find materials that best suited for the environment.
Excellent. Thank you very much. Cheers for that, Bill. Okay, I've got 100 questions to ask you after this. Otherwise, we'll be here all day. So we can all thank Joven in the usual way. Thank you very much. And just like that, we've come to the end. we've got one more presentation first. So unfortunately, our presenter today wasn't able to attend, so he's done a recorded presentation. Hopefully you can all enjoy it. And this presentation is on corrosion challenges and related opportunities and arduous next generation low carbon energy systems, focusing specifically on solar and e-solar by Dr. Frederick Pessu. Just give a bit of background. Dr. Pessu is a lecturer in corrosion and based in the Institute of Functional Services at the University of Leeds. He holds a BA in chemical engineering and MSc and PhD in corrosion engineering at the University of Leeds as well. He's been working in the area of corrosion science and engineering since 2009. His research interest is focused on the fundamental understanding and characterization of materials performance in arduous corrosion systems, including renewable and low carbon energy production systems that support energy decarbonization. Specifically focusing on a couple of areas, including molten salt corrosion on concentrated solar power generation plants and molten salt reactors, fixing low-growth corrosion in CO2 H2S environments, and design and development of bespoke experimental methods and corrosion studies. And Frederick is also a chartered engineer, a member of IMechE Institute of Corrosion and the CEO of Corrosion Technologies. So unfortunately, as part of the recording, you're going to have to really do that all over again. But unfortunately, you can enjoy the presentation.
Yeah. A lot of things open here, so. Nothing is working.
Sorry, computers just crashed, so we're just trying to get it back up.
Lost connection to the
Internet. No, it's not internet. I think it's just.
On and off again.
Yeah, that's probably.
Or we can put it on like the other tools and give the online link to everyone to watch it there.
Yeah,
Because
because it's
on
already
it
shared uploaded.
doesn't
Yeah,
really sound right.
yeah.
What's that say?
good.
Maybe you can add it to the bonus material.
Don't know, because the recording, nobody's gonna take the question. It's just gonna be just watching cinema at the end of the day. That's really nice.
Seems like I have to restart. Yeah, we can.
High level ambitious statements that you said.
How are you connected to Zoom?
So now I just have to do back to doing the Zoom. So